Okay, thank you very much to the organizers for the invitation to speak today. Thank you, Christelle, for that really nice introduction. I wasn't expecting that. I want to start by giving up the first portion of my talk just for you all to take a look at the following statement. This has been adapted for slides by Juliette Bruce from a statement which you can find online by Carrie Eaton, and I can provide the link to that in a moment, but I don't have it handy at the moment. Also in the chat, you'll find a link to my actual slides for the talk, which is also hosted on my website. So I'm not going to read the whole statement, but I do want to focus especially on the bottom paragraph to the broader mathematics community, and I'll say even to my white mathematical colleagues. This is an issue that we have not taken seriously. We are failing the people who the top paragraph is directed to, and we cannot really be called mathematicians, and we certainly cannot be effective colleagues of mathematicians if we cannot take this seriously and if we cannot throw our all into fixing this issue, into supporting anti-racist efforts, and into holding ourselves much more accountable than we are. So if you would like a link to Carrie Eaton's blog post or that this was adapted from, or if you'd like a copy of these slides, you can contact me after the talk. So I'm going to figure out how to do the thing. I'm new to WebEx, so pardon me if anything is really slow or clunky, but here is my talk. I think I should have about 18 minutes left or something. We'll end on time. So I'm going to tell you about my thesis project and something that's still ongoing, which if I get to at the end, I can tell you a bit about what the current status of this problem is. So just to kind of start from some common language together, a problem that we often run into in math is from topology to geometry to algebra, is we lose all sorts of information when we take quotients of things. And actually, this is related to when we have singularities of our objects. Excuse me. But I'm going to focus on the quotient aspect of this today. So you can think of a parabola. Maybe you'll fold over along a symmetry of the parabola and then glue together and get a new space, a new set of points. But we lost a whole bunch of the beautiful information contained in that parabola. So one way that some mathematicians solve this problem, including myself, is to keep track of that lost information using the notion of orbifold in topology and geometry, which is a sort of intuitive notion I'll explain in a moment, or using the notion of a stack, which is a lot more abstract and algebraic, but in my opinion is the more robust of the two terms, and there's a lot of interplay between the two. So mysteriously, I will denote the notion of keeping track of something using a stack by labeling that vertex point with a 2 when we quotient. To be more specific, if we take this to be our plane curve y squared minus x equals 0, then treating this as a stack or somehow stackifying the problem, we'll remember things like the symmetry or the automorphism of the curve, which sends y to negative y, and we'll do so using groupoids. And if you know what a groupoid is, then this diagram probably already tells you what the solution method is. If you don't know what a groupoid is, it's just a way of sort of dressing up our diagram to keep track of these extra symmetries. So I'm mostly going to focus on curves today because that's the main problem I'm interested in. And the problem a little more concretely is to classify Stacky curves, which sometimes are called orbifold curves, in characteristic P. And if you'd like to read more about there's a preprint available on arXiv, which is coming from part of my thesis. So for the more topological version of this problem, a complex orbifold is a type of topological space which behaves sort of like a manifold in the sense that around each point there's a chart or multiple charts, and each chart looks like complex, I'll say for complex orbifolds, complex n space Cn mod the action of a finite group Gi. So about this point that's shaded with a neighborhood that's tan, you can think of maybe it has a threefold symmetry on its complex chart. So that would be an example of an orbifold point, or a point in an orbifold. There's a different notion in geometry, in algebraic geometry, or in algebra, which is that of an algebraic stack. And not all stacks are exactly like our friendly complex orbifolds, but an important class of these stacks can be viewed as taking an underlying smooth variety or a smooth scheme and attaching a finite automorphism group at each point. If you think back to that parabola we had, you can imagine what the finite automorphism groups are at each point in that case. So for example, around our threefold symmetry point, we could just attach the abstract data of the group Zmon3. We could attach at different points, different finite groups. We could attach non-abelian groups if we feel like it. The biggest finite automorphism group I can think of is the monster group. So we can attach all of that data. It'll turn out that only cyclic groups really show up in the end, at least in characteristic 0. So I'm going to focus on curves for the rest of the talk, but just keep in mind that all of this can be done in arbitrary dimension. A motivating example for me originally, and still ongoing in some sense, is the moduli space of complex elliptic curves is a natural Stacky, an example of a Stacky curve. So as an underlying scheme or an algebraic curve, it is the complex plane P1, sorry, the complex, whatever you call, the Riemann sphere P1. And as a stack, or rather, the perspective is that we should view this as a stack where every point has a Zmon2 automorphism group coming from the hyperelliptic involution on the Weierstrass equation. And then at two particular points corresponding to J invariance 0 and 1728, which is the password for this conference, we have a Zmon6 stable automorphism group and a Zmon4 automorphism group. And the advantage of viewing this as a not just complex curve, but as a complex Stacky curve, is that you can directly deduce dimension formulas for modular forms using a certain version of Riemann-Roch that counts Stacky points in addition to just the underlying points. So all of these different automorphism groups will show up in your Riemann-Roch formula. So the goal for me is to classify Stacky curves in characteristic P. And one of the main obstacles, which I already mentioned, that we need to overcome, excuse me, is that in characteristic 0, so for example, over the complex numbers, this is fairly classical, but I'll talk about a recent result which sort of captures the full classification in characteristic 0. That local structure, though, is determined by a cyclic group action. So all I need to worry about is essentially the order of a cyclic group. That number 3 or 6 or whatever the other ones were determines the local behavior. In characteristic P, it turns out this is not enough, that even if you have a cyclic automorphism group at a particular point, you need more information than just the order of that cyclic group in order to determine the, let's say, the isomorphism type of the Stacky curve locally. So some results in the direction of classification are that, first of all, if we want to obtain Stacky curves, one way to do it is to take quotients of things that we already have out there. So if you take a Galois P cover of curves in characteristic P, then taking the quotient stack defines what's called an Artin-Schreier root stack structure. And this is new. This is something that I've introduced recently. And I'll talk more about this for the rest of the talk. And one of the results is that every P cover of curves factors, at least in some local sense, through an Artin-Schreier root stack. On the other hand, if we just start with a Stacky curve that we don't know it came from a quotient or not, at any point with an order P automorphism group, you can build a neighborhood around that point that is isomorphic to one of these Artin-Schreier root stacks. So namely, that Stacky structure came from a specific type of quotient structure. And then finally, for any algebraic curve, this actually proves that there are infinitely many non-isomorphic stacks and even Deligne-Mumford stacks that have that underlying curve X and degree P automorphism groups at the same set of points, but again, they're non-isomorphic. So there's something about the Artin-Schreier root stack that can be varied in families and gives you non-isomorphic curves.
Andrew, may I ask? You talked about some conditions between, like for the charts. Does that include compatibility between those groups at each point?
Yeah, absolutely. So I'm really understating the definition of orbifold, but yes, you would have an induced, imagine trying to write down charts and then including group actions, you'd have equivariant transition maps in particular. So that's part of the data that I'm sort of suppressing here, but yeah, good question.
Thank you.
So let me talk a little bit about characteristic 0. For me, as an arithmetic arithmetic geometer of sorts, I usually look to topology for inspiration. And in characteristic zero, a lot of algebraic geometry, especially this type of algebraic geometry, is not only well known, but fairly topological in nature. So in characteristic zero, as I said, the automorphism groups, which I'll sometimes call these stabilizer groups, are all cyclic. So it turns out that you can locally model the structure of a Stacky curve, or in general, a stack with certain properties, by a root stack. And what a root stack is you can algebraically construct this using a ring extension. If K is an underlying field, or even K is any ring, then if we adjoin the nth root of an element alpha, this is how you do this algebraically, there's a natural action of the group of nth roots of unity. And I might want to say algebraically closed so that I have all nth roots of unity defined or something. But in any case, this is just sort of a murky picture for the moment. But this is the way to adjoin things or to get nth power structure algebraically in characteristic zero. You want to think of this geometrically. If you have a neighborhood of your curve, and you want to construct an nth root structure or a power n structure on such a neighborhood, then you want to take a degree n cover. And locally, degree n covers are all given by such an algebraic equation as covers of curves. So you should think of this as a degree n branched cover, maybe branched at the zero locus of that element alpha. But we're also keeping track of the action of mu n using groupoids. So that goes back to that parabola picture that I started with. So a rigorous definition of this structure is what's called a root stack, and this was introduced by Kobin and independently by Abramovich, Olson, and Vistali about 12 to 13 years ago. So in this definition, we start with a scheme and a line bundle on that scheme, which has a section S, or equivalently, we can start with an effective divisor. And to that data, we associate the nth root stack of X along the data L, comma S. And it's defined to be the fiber product of the following diagram. So the key parts of the diagram here are that pairs LS, or equivalently effective divisors on your scheme X, determine maps or are classified by maps into the quotient stack A1 mod GM. And the affine line A1 and GM both possess a degree n map, which just sends the coordinate X to X raised to the N. And it turns out this is compatible with the GM action. It's equivariant to get an induced map on this quotient stack. And all you need to know about this quotient stack, if you haven't seen stacks before, is that this is a space that classifies pairs L, S. But there's a little more to say about this if you're curious.
Andrew, can I ask?
Yeah.
What do the brackets mean?
The brackets just mean the stack quotient rather than the scheme quotient, because you can take A1 mod out by the GM action, the multiplicative action, and then you just get a point. But here it's a Stacky point.
Thank you.
Thanks. So the way to interpret this, if we map a line bundle and section pair LS into A1 mod GM, and we pull back along this degree n map, then what we're doing is artificially or abstractly introducing a tensor nth root of that pair LS. So in other words, we're introducing a pair MT, line bundle and section, so that M to the N is L and T to the N is S after pulling back to this new stack. So this is a way of introducing sort of abstract nth roots of line bundles and their sections. So the more rigorous result in the direction of classification was by Anton Gerashenko and Matt Satriano about 5 years ago, which one version of their theorem says that every smooth, separated, tame Deligne-Mumford stack of finite type, and the tame condition involves potentially being in characteristic 0 or just not having certain divisibility conditions in characteristic P, which I'll mention in a moment. But given such a Deligne-Mumford stack of finite type with trivial generic stabilizer, that at any such stack is a root stack over its core space, or is an iterated root stack, which I'm just going to call a root stack. So there's a bit of I'm suppressing a bit of things with this asterisk, but you can ask me later about that. So for our purposes, if we start with a tame Stacky curve, and tame for us means that the characteristic of the ground field does not divide any of the orders of the automorphism groups, so in particular, this is true in characteristic 0, then tame Stacky curves are completely described. They're classified up to isomorphism by their underlying algebraic curve, which is called their core space, and a finite list of numbers corresponding to the orders of those groups at every point. So because we're assuming Stacky, and I guess I haven't said this officially, but I'll take my Stacky curves to have trivial generic stabilizer, meaning they're on a dense open, they are just a scheme. Then we just have a finite collection of points with non-trivial groups attached. Now the question is, if p equals 5, for example, two of my stabilizer groups might be divisible by 5. What happens with wild Stacky curves, which is the more general case when we don't have that tame condition? So in trying to classify these in a similar fashion to how Gerashenko and Satriano do it and how some other authors have handled tame Stacky curves, there are a couple issues that we need to deal with. So one is that the groups may not even be cyclic or even abelian, and for the full story on that, talk to me later, but this is difficult and not solved yet. But even for cyclic covers, just for ordinary algebraic curves, for varieties, for field extensions, cyclic Z mod P to the n covers occur in non-isomorphic families. So there's something to deal with there. And the main trouble for us for the geometry is that root stacks don't work. And there's a couple issues with taking a pth power or a pth root in characteristic P that you may be familiar with. But the main issue that it boils down to is that x raised to the n map is a huge problem if n is divisible by p. And even if n equals p, raising to the p in characteristic P is a problem. But for characteristic P geometers like me, it's actually a good problem because this is how we get papers in journals and get invited to speak at conferences. So I love characteristic P problems. I'm going to focus specifically on the cyclic order P case. So when our Stacky curve or our quotient object has some order P symmetry, and we can actually give it classification in this case. So if you remember back to our root stacks by Cadman and Abramovich, Olson, and Vistoli, that had the local structure given by a degree n branched cover, then it turns out for a Z mod P cover in characteristic P, the right notion is that of an Artenschreier cover, in which we replace that y to the n equals some element by the equation y to the p minus y equals some element. The key word here is étal. You want an étal degree P cover, and you can check that away from the zero locus of F, this will be étal. So this is like the right notion of branched P cover. Artenschreier theory classifies such covers, and there's an extra invariant called the ramification jump, where if I picked this function f of x to be x raised to the m, then varying this m gives me non-isomorphic covers some of the time. There are relations among these. But in any case, for us, this suggests replacing that root stack structure, which was a degree n, maybe a characteristic 0 phenomenon, or at least a tame phenomenon, with a quotient stack that is locally of the form, this degree P cover mod a certain Z mod P action, which in this case is additive, and this is all coming from, and basically the Artenschreier theory is an additive version of Krummer theory in characteristic P. So how do we do this? Let's take our kind of defining diagram for the root stack, and I'm also watching my time. I think I want to double check that it should be 1:55 when I can end, according to when we started, but please correct me if I'm wrong. So let's start with our diagram in terms of line bundles and sections and pulling back along this degree n map. We're not allowed to take nth powers anymore if n equals p. So instead, we can replace this A1 mod GM with, first of all, we can replace A1 with a compactification of A1, that's the projective line P1, and that admits an action by the additive group GA, that's just another copy of A1 acting as a group. And it turns out that there's a natural degree P map, which I've written down in coordinates here, but this is on one affine patch, the Artenschreier map, x goes to x to the p minus x. This quotient stack, it turns out, classifies not just a line bundle and section, but also another section that doesn't vanish simultaneously with S. And will denote that pullback by Weierstrass P inverse of the data. So basically the pullback of the data along this map. And the official definition is a little complicated, so here's a glimpse of what it is. But in order to classify Stacky curves, I've introduced the parallel notion in characteristic P of an Ardenshire root stack. This was an example of one of these, where the root stack needs to take into account that ramification jump, that extra ramification invariant of degree P covers in characteristic P. So specifically, what you need to do to build one of these structures is start with a line bundle and two sections this time. One of them a section of L, and the other one a section of the mth tensor power of L, where a priori you've declared what your ramification jump is expected to be. And in order to define your Ardenshire root stack, you write down the right degree P map on a certain weighted version of P1, which here P1M is a weighted projective line with weight M in the second coordinate. If you've seen these before, or rather, if you haven't seen these before, you're essentially just introducing Stacky structure directly to the weighted projective line, just at the point at infinity. And if you pull back along this degree P map, you get a new structure, which we're calling the Ardenshire root stack. So let me skip ahead and tell you a bit about just how the classification results really look as theorems, and then I'll close with a bit about where things are going next and open for questions. So the key theorem that gets things rolling is that Galois covers of curves with Z mod P structure locally can be factored through Ardenshire root stacks. And exactly the way you do this is by looking at the quotient structure of this top curve Y, the covering curve, by the Z mod P action of the inertia group, and then relate that to this Ardenshire root stack directly. And there's a way to do this basically using base cases and getting your way up to any curve. And the more interesting result, and what I was aiming for originally, something along the lines of this, is that a Stacky curve with order P Stacky structure, it all locally looks like one of these Ardenshire root stacks. And the whole key here now is that the combinatorics of these Ardenshire root stacks, the fact that they're in some ways determined up to isomorphism by that jump M, allows you to bring questions of ramification and the idea of the difference between different order P quotient structures and characteristic P to bear on these stacks. So I'm going to leave this up as my final slide. So I do want to thank you for your time. And again, for the invitation to speak today. There's a bit more going on with higher order structures and characteristic P that requires a lot more, for me, more interesting techniques and tools. But this is forthcoming at this point, and I'd love to talk about it more in the hallway if you're curious. So thanks again.